Let's start our next session. Also, we have one invited speaker. His topic also related with ultrasound. And Liudas Mazeika, he is director of Ultrasonic Institute, and will present topic ultrasonic measurements, trends, problems, and solutions.
Hello, everybody. Welcome you to gather there in Palanga, very nice Lithuanian city near the sea, and I hope there will be very good atmosphere, scientific atmosphere inside conference, and good weather outside, maybe with rain a little bit. But so my speak will be a little bit different. I will come from some basic of ultrasound and then illustrate with some different examples of my experience. And I am from Ultrasound Institute in Kaunas University of Technology, and this is not new. I will say very old institute concerning ultrasound, because it's established maybe 55 years ago. So as for ultrasonic field, it's very old. It's because ultrasound in general is probably first applications I will mention appears in somewhere in Second War for location of submarines and so on. So the first, what is ultrasound? It's me talking without this. Yes, and ultrasound officially say that is acoustic waves higher than 20 kilohertz. In general, it's very, very, very relative, because people can hear, some people hear, especially young, a little bit higher. All the people hear a little lower. But it's like to say official definition of ultrasonic waves. And however, they goes very high. Now there is such technique as acoustic microscopy, which goes probably up to even 1 gigahertz. It's acoustic ultrasonic waves, but it's very special application. And of course, this is pressure waves in gases and liquids, and elastic waves in solid materials. So, but not humans invented ultrasound. It already existed in nature. It's one of animals which use it is dolphins, which have communication, and probably they locate the target or some obstacles. And another one is bats. Is also they used widely. They can fly in the darkness and just to locate all situation with ultrasound. And I will say that these two equipments probably in some sense much have advanced than we have now ultrasonic equipments. In some sense, we have of course developed very different instruments which, like to say, goes further from them. But in some sense, they are very, very, very innovative. And the first application of ultrasound in humans is probably started from detection of submarines and ships from submarines, depth of the seas and lakes. And so this is first application. And the advantage of ultrasound is that can penetrate through not transparent for light materials. It's like to say key advantage of ultrasonic waves. And if we look where it's very briefly where it's widely used, it's two areas. I think for public probably one is more known, is medicine. I think women probably all know about that, or at least they will know in future. But anyway, but it's not detection of babies, but it's heard and it's very, very widely used in medicine diagnostics. And another area is industry, and there's a little bit very different objects. In medicine, there is very concentration because all we are the same for ultrasound, more or less. It's not exactly. For example, blood, ultrasonic properties of blood, women's and men's are slightly different, but very little. But in general, for ultrasound, something very close to water. except of course bones, which are some composite material like today. It's a completely different situation in industry, because there's a plenty of materials. It's metals, plastics, even metals, they are very different. For example, conventional steel is very transparent, but the so-called stainless steels, austenitic steels, which can have very, very big grains, and in this case, they are very attenuating or scattering. So also it's composite materials, it's some viscose materials. So in industry there's plenty, much wider area, much wider space for materials, and because of that, it's much more different instruments. In medicine, they are concentrated for imaging and for some measurements in biology. In industry, it's very, very, very widely. So the next question is why it's necessary to look into these metals. Why to look in our body, we know. We want to be healthy, not to have sickness or so on, but why we look? And one of the widest field of ultrasonic application is detection of defects, different defects. And this is, like to say, very well-known examples of accidents. There are plenty of them. And in all cases, they are checking for defects, but not always succeeding. So this is an accident of Intercity Express train in Germany. It's at 200 kilometers per hour, he crashed. And the reason was defect in the wheel, just defect, small one, which lead, of course there's some other conditions we have been, but anyway, primarily is defect. Another is ultrasound. We have some accident in our oil refinery, very close to there, I don't know, 50, 60 kilometers somewhere, 70 maybe kilometers away. And it was a big fire, and the problem was also some corrosion, not checked before. So not to check usually costs very big money for industry. And another one is accident, is maybe very successful accident. Nobody have been damaged. It's in Kaunas. The bridge was dropped down a little bit, not completely, but a little bit, because there's some steel holders which just crashed. And why crashed? Not badly calculated, but just appears some defect which is developing. Another feature why is inspected nuclear power plants, pressure vessels, different things, that all defects are keen to develop, to grow, because cracks is very narrow. At this very end, they have some concentration of tension, grows, and fails. So now it's. I mainly will talk about industrial applications, not about medicine, because about medicine, even in this case, I can talk for many hours, for up to the Wednesday, but maybe not this time. So it's just example that there is some transducers which propagate ultrasound inside, and if they're defect, you get detecting some non-uniformity, and you can estimate and so on. So it's possible to detect some non-uniformities, defects, to measure properties, and I will say that it's only method which directly related to elastic properties. Elastic properties is strength, density, different things. So it's only method. There's other methods can be used. Sometimes electromagnetic, I don't know, some independent measurements. But method, because properties of ultrasonic waves directly depend on material elastic properties. So there's a changes in material properties, there's change in our signals. So, and another thing, advantage, that this is it is non-destructive method. It's not necessary to cut. I do not speak about medicine, but it's in industry, it's not need to cut piece, to take piece, to measure, is it strength, is it defect, to look inside. So, on the other hand, ultrasonic measurements looks very simple. We have already previous presentation that you have transmitter, receiver, one side or reflected to the same side, and just measure signals And from these signals, it's necessary to measure, for example, time of light, attenuation or scattering, sound velocity, structural noise, for example, is related with scattering, propagation direction, and from these values, you can estimate, I don't know, properties of material, even of liquids, if there are some changes in content of materials. Probably you all already used, for example, you know, thunderstorms and lightning, yes? How far they are? Usually people say that, okay, you see lightning and then calculate 1, 2, 3, 4, 5, and then divided by 3 up to the thunderstorm. And the distance is you're getting the distance in kilometers. Why? Because ultrasound velocity in the air is about 340 meters per second. So 1 kilometer is passed around 3 seconds. So we can easily, ultrasonic measurements, sonic measurements, but the same. Just question about accuracy. And from these parameters, you're getting elastic properties, viscosity, dimensions of the object. For example, you're getting echo, you're getting distance, density of material, non-uniformities. For example, you're detecting that in some place ultrasound velocity is a little bit different from another. What does it mean? It means that there is some difference in some properties. Why? It's not ultrasonic question. Usually there is some structure integrity people which determines what can happen there. Temperature, pressure, and so on. So just advantages and field of application very briefly. So first one is enables to look inside the objects. The second one is very important, non-dangerous. For example, even for humans, both ultrasound and X-rays are used, but usually do not enable to use X-rays, photos, or tomography very frequently, because X-rays are dangerous. Especially in industry, in order to get image, like to say X-ray image of some metal plate or object, energy used is much more higher. In this case, in general, is dangerous even for life. So yes, X-rays also used to look into the non-transparent materials, but it's very restricted where it can be used. So it's problems with safety. Also, it enables online measurement. You can put some instrument, and even you can put transducers inside the object and to monitor what happens during, I don't know, exploitation or just performance of some. And also it's that it's possible to investigate in micro and micro scale. I mean macro, for example, what ultrasonic ear couplet through ear usually have lower frequencies, 40 kilohertz to 200 kilohertz, but it's related to wavelengths. So if we detect something, it will be at the range of wavelengths corresponding and longer, bigger object. On the other hand, for example, in our institute, we have acoustic microscope, which works up to 230 megahertz. And in this case, wavelengths of ultrasonic waves is in the range of 6 micrometers. So in general, you can scan to look into the electronic chip to determine what is inside. Is it not, like we say, cracked or something like that? And resolution is extremely high. Also, there is a field application. It's non-destructive testing and monitoring due to safety, ecology, and even due to finances. Assessment of material properties, medicine, diagnostic imaging, process monitoring. Process monitoring, for example, measurement of manufacturing of plastics, flow measurements, even, for example, heat energy measurements. There's ultrasonic meters which measure how many energy you're using for heating of your house. It's commercially available instruments. So, on the other hand, I said that ultrasonic measurements looks very simple, but inside it contains very many sciences, and it's physics, it's mathematics, it's electronics, it's no way without it, and it's informatics, especially in last year, because you're getting signals, what to do with them. It's not electronic operate with them, it's informatics. And like to say in middle, like to say measurements, because usually you need to assess what you are measuring, not just to get some value. And also there's very important two things, is modeling and signal processing. Modeling is because it's impossible to understand what happens inside structure without modeling. So if to look at the ultrasonic measurements, like to say in more complicated way, so usually we can have many transmitters, not single one, and many receivers, and some medium, which is space. It means x, y, z, and time for like to say for unknowns. And this is very important, because when we excite transducer, we excite by electrical signal, which is in principle just function of time. So the ultrasound propagates in space, and then we're receiving and gave back to the one variable, like we say. So it's very complicated transformation, and it affects in different wave measurement results. And so its medium is at first is 3D pressure wave or 3D longitudinal axial waves in solids. It can be, if we talk about guided waves, what propagates in plates, in bars, in pipes. There's so-called guided waves, and there's not just longitudinal or shear waves. It's combination of them, and it's so-called multimodal media. It propagates very different modes. And diffraction, refraction, attenuation, scattering, dispersion is also dispersion. If we have guided waves, the velocity of them depends on frequency. If we talk about longitudinal shear waves, it's no dependency, almost. It's just the same. It's for metals, for plastics even, there's some dependency, but it depends how accurately measuring. But for guided waves, it's very strong dependence for each mode. And also some things like complex object geometry, extreme conditions, and other things. They affect our signals, and it's necessary to decide what to do with them. So if we look at the very easy at four main parts of ultrasonic, any ultrasonic system, air couplet, medicine, or industry. It's electronic, ultrasonic transducers, scanner, mechanical scanner maybe, and software. Which so if last tendencies, if we look what happens in the world in the field of electronics for ultrasound, so what we say that one thing is essential reduction in dimensions of it. It becomes smaller and smaller. Number of channels, it means that you can connect, I will say later, many transducers or phase arrays, so-called. Integrated units, it means that you can integrate somewhere into the instrument in technology, very small, which performs measurements. And for example, battery powered, for example, if I remember correctly, flow measurement instrument, it doesn't require power supply from the set, but it just works for 5 years or something like that. On batteries, you no need to change. And it's electronics in general. And also price reducing, but to the limits. Because in most cases, it's not like to say for white peoples, but for industry, for energy institutions. So it's still not very, very cheap in medicine, including medicine. Cheapest maybe there's a distance measurements, ultrasonic is tens of euros probably. There's sonars for fishing bands, which look how much fish behind surface. So there are some hundreds of euros, but in general, its instruments are not very cheap. It's just like to say one of examples is company Lecure Electronic announced that they have ultrasonic 2-channel system, which looks like a stick, memory stick. That's all. This is all complete system. Of course, if we go into detail, probably the gain not very big, a little bit noisy, different things. So it's not the case that okay, we have small system and bigger system do not require it. Also, we have usually big tendency to put all menu on the laptop, not laptop, but on phone or tablet. But there is also, I will say, doubt. We have project. I will show later. It's an example of that. But the tablets are not powerful enough for signal processing. So there's still problems to make, like to say, your experiment carrying out and just look everywhere. Not so easy. Now another instrument is from M2M system. By the way, it was developed under one project which we participate together. We're not worked on this instrument, but anyway, but it's just example. It's not say that it's only one company. There's many companies, but it's again all incorporated. It's very friendly. It's very forced to use operator all necessary steps. And one of the version was submergible, or you can put it into water and to work without like to say, afraid that it will be broken, something like that. Now ultrasonic transducers, and if to look what is again tendencies. The first one is that there is a phase array. Phase array, it means we have not single element, but we have many elements, and by exciting them with corresponding delay, we can focus at different distances. In general, there's an image what we can steer beam in different things. It's very widely used in medicine. It's used in industry also, but with industry problems that you cannot usually scan only one place. You have some weld, some pipe, and anyway, even with phase array, you need to go further to scan object to look. It's not enough for medicine. It's mostly case. It's just electronic phase array, and doctor has mechanical scanner, which looks so it's like this. Another field is ear couplet, because not all materials you can be vetted. Vetted because what in previous presentation you understand that is very big losses in ear couplers. So if possible to avoid the use, but it's not convenient. So for ear couplet there is a very huge attempts from various companies to use lasers for excitation and for reception. And there's such systems exist, but price very big, one thing. Another, they are very sensitive to surface conditions. So on some materials, okay, but if you can imagine industry have some a little bit dirty or some roughness and so on, so it doesn't work. Another, there is integrated with very thin, which you can incorporate into material. And environment resistance is, okay, just some limitation of phase array. It's two limitations. If to go down, it's very complicated to make many elements. If to go up into the frequency, also limitations. So if we talk about, for example, microscopy, acoustic microscopy, there's no such phase arrays till now. And now about a little environment. This is our development. Is ultrasonic transducer, which can operate at temperatures up to 450 degrees Celsius, can be submerged in liquid lead bismuth alloy. In general, they were developed for operation into the new types of reactors which are cooled by lead bismuth alloy. So additionally, there's a strong radiation, and there was big problem not only to survive. At the beginning, when you have developing, it was seemed that okay, piezoelectricity, all effects die. Curie point is where piezo effect is like disseminated, but there's other problems such as coupling. For example, if you transferring this ultrasonic wave into lead bismuth alloy, so if it is coupling well, it starts to eat even metal, because it's chemically aggressive, very aggressive. So it's just one of examples. And this is, by the way, measured temperature in this alloy using these transducers in our laboratory. Another application is ultrasonic transducers, which used for online monitoring of liquid plastics. It's again high pressure, high temperature. Problem, but where a problem arises is, for example, you manufacturing plastics, and now is using recycled plastics. And the recycled, a little polluted, it's not very pure, so you need to monitor density, viscosity, otherwise your product will be not qualified, like to say. Now, as I said, it's very complicated to avoid mechanical scanner, but it's probably a completely another topic, because it's very, very wide. For each object you need for some another scanner, because geometry, object, what to put, and so on. So this is very interesting example from Inete company from Croatia. We have project with them together, and this is robot which can go into the pipe and travel around and to inspect the pipe from inside. So it's like to say, you see like worms some. And of course, in sense of scanners, tendency is to develop autonomous. The dream, again, if you, for example, have some object, you have some welded plates or something you want to test, the dream is to put scanner and go for coffee. Scanner moving by itself. But it's, till now, it's too complicated. There are some companies which start to make, but usually they are controlled by humans, not autonomous. Now software, there's plenty of companies which use and develop different software for modeling in ultrasonic field and for data analysis and presentation. One of them is so-called Extender, which you have developed some so-called Shiba, big like to say software, which big code, which can be used for different non-destructive testing areas, including nuclear, and is certified, and you can get with them different images of ultrasonic signals. You can filter, you can put different transducers, parameters, geometries, and so on. It's very widely used. However, it's not always is possible to use this. If you're getting new techniques, new measurement techniques, or you're getting new materials, it doesn't cover. So just brief need of modeling and signal processing. It's the first one is, of course, ultrasound is invisible, and it's necessary to understand how it propagates, and you want to see, so you need modeling, and to determine irregularities, and afterwards with experiments. And problems to develop methods, because it's very, like to say, models are analytical and numerical. Analytical is, like to say, for some very, very limited cases. Numerical, very good, but you're getting very many sampling points. Well, let's assume very easy task. It's you want to scan 3D area, just 100 is cubic. It's 10^6, and if you in each case have signal, it's gigabytes of information. It's crazy. So the same for modeling and both for signal processing. So it's key issue to get model which is capable to solve this task under the limited resources of computers. It sounds very crazy, but because computer resources grows very fast, but anyway, wishes also goes very fast. This is a very, very easy example. It's modeling of, for example, of ultrasonic field of bipolar transducer. When transducer is created using not one element, but two elements. So with opposite polarity. And also there are some wave propagation in pipes because you're getting very many reflections. So it's just example, very easy examples to what is necessary to develop in some cases. Another much more complicated related to complex geometry of objects. It was developed ultrasonic system, but there you see a transducer or set of transducer who looks in very complicated object. In general, this is mirror reactor interior. It's a real image, and then you can possible to scan any you want. It's our developments. You can scan in any curves in any positions with any number of transducers, and to get image of the object, what it will be, you can expect in reality will be. And without such models, impossible, for example, to develop technique which should operate in liquid lead-based metal alloy, because experiment is too costly. Another thing that, for example, is quite easy, but is so-called nozzle. Is junction of two pipes. Sounds very simple, but in general, it's junction of two cylinders. And geometry 3D is very complicated. And as you know, there is a Snell's law, and when you put a transducer to determine where it's looking, becomes very complicated. By the way, just but now we have very small contract developing simple calculations to estimate where transducer should position in order to look in correct way. Now some brief signal about signal processing. Usually we're getting signal, and in principle it's looks very simple. We have excitation signal, we have transfer function of medium, and we're getting the signal. But usually the task to determine this, not to use, but to determine in signal processing. So in general, we want to extract how medium transfers our signal, and this is inverse task. So in direct way, it's impossible to solve. So many things necessary to do to overcome this. It's just some example of experiments. How propagate ultrasonic waves in plate. Another instrument what can be achieved with signal processing. For example, you know very big storage tanks, yes? And due to ecological reasons, they need to be tested. And the walls, it's easy to test. You can come and check, is it not corroded? But how to check bottom? Bottom, you need to take off all content of it, I don't know, oil, some gasoline or something like that, and to clear, to come in, and it's dangerous, and then to inspect, and it's done. But the price of inspection, of checking for defects, is maybe 10% from total price, because to clean, to everything, to empty it, is much more costly than inspection in itself. So there was a technique which developed also by propagating ultrasonic guided wave through tank floor from all sides in many directions. You're acquiring many signals, and afterwards you're getting some image where red zones are related to higher attenuation, and high attenuation is related to corrosion. So in general, you can reconstruct the condition of tank floor without going inside. Another very interesting also project is just ended. I don't know, is that there's just the detectors of fire, but there's a fire sprinkler system. It means that there probably, maybe, I don't know, but should be pipes with water, which prepared, if there's fire, they start to put water or gases, I will say. So these pipes should be tested time to time, not each day, but 10 years, 5 years, because if it is not proper way, it cannot work, or it can be even leakage on the computer, on, I don't know, on some other goods in shops or so on. So it's necessary to test, to check it. Is it pipes are correct? So this is my colleagues from project. There's a sample 6-meter pipe just to check for developed techniques to detect defects. They're drilling some hole, you see there, and there is an image of this is angles, but in general it's 16 signals measured. And if you look, the signals look crazy. If to look like to say, assume that the defect should be somewhere in this. This signal was in front of this hole. Nothing. You have some crazy. Another thing that if we look, is guided wave. If pipes, you're getting not like in beginning of my presentation. Oh, I'm getting echo. It's very clear. You're getting many echoes from one end to another end and so on. If you zoom this area, the true signal from this hole, but this one. And this is at least 30, 40 dB from the comparing to the 40 dB. It's 100th of time, yes. And so it's very tiny signals. How to operate them? Of course, there's a complex algorithm which filters, selects many things, and after that we're getting very precise position of this hole and from distance. And additionally, at relatively low frequencies, it's not high frequency for small defects, but this is somewhere about 50, 40 kilohertz. And not only one, and what tomographic reconstruction enables to determine even distributed. We drilled not single, but many. So technique, what can be obtained with only signal processing, because technique itself, it's used already. It's me. It's also interesting, the instrument, the technique was tested in Cambridge Library, in archives, so it's a very, very interesting place, by the way. Amazing how many literatures you can find from history. It's very amazing. Another thing is, for example, now it's tendency to change steel pipes into the plastic. They are more long-term, can be longer exploited, and they do not corroding inside and so on. And for heating pipes, I think in Kaunas now, very many places they are digging, changing, and these plates, these pipes are joined. There's several techniques, but most widely used is some called coupler with wires, and it's heated and just melted to the pipe. So it's a technique sounds very easy. But you can imagine that it's not like to say you're making factory and after that checking. It's in trench. You're adding another pipe, checking, and you should put the ground on. You cannot wait for some days. And in this case, the people which check should be somewhere there. So they need to check very fast. And it was topic from another project. And the problem is that if you check just on one line, you're getting image like this. This is heating wires after that, and this is correct weld, because if it is bad, you should see there some reflections. It's not welded. But when you're checking all pipe, you're getting about 700, 2000, depending on diameter, ultrasonic image. So if you sit and just check everything, it will goes time running. The people are there just smoking, eating, and doing nothing. So it's not efficient. And so it was developed technique, automatic just analysis of signals and data, which enables to reconstruct. This is, of course, from sample. Green lines, it detects even heating wires and separates them. Then it detects delaminations, and afterwards it makes some map, like to say, which shows where is defect in automatic wave without influence of operator, just push a button. Of course, not in always. It's like to say we say that we need traffic lights: green, yellow, and red. Red bad, yellow, green good, yellow call man. let's say, which can explain. And the last one may be some interesting also in signal processing. There was problem with so-called creep damage. If steel pipes are exposed in power plants, it was not in nuclear but in conventional, cool heated power plant. If steel exposed to the high pressure and temperature, it starts to a little to creep. And these defects starts to appear from I don't know, micro scale, micro cavities, then they join the micro cracks, and of course grows and breaks. And even we ask in power plant, okay, but it's conventional power plant, okay, pipe breaks, you stopping, repairing, and so why to check before very early and to know? Answer very easy. How long they will stop and start again? 2 weeks. Each week, 300,000 pounds. So it was in UK. So calculating, yes, better to check before. So it's just an example, one sample, but maybe, and then you detect in plenty of cracks. I will show a little later. But again, I previously showed very little signals. You see in this image, it's original signals measured in our laboratory on test sample. You see this is surface reflection and nothing. After smoothing, compensation of the mismatch of axis, removing of top surface reflection, we can see some sign patterns in general, which indicate that there are some reflectors inside, which moves when we rotate according tomographic reconstruction. So if we just analyze this area, we're getting image like this, where it's possible very easy to see that this is parent metal, one structure. This is a more noisy in sense of ultrasonic signal, it's weld material, and inside there's some so-called heat effector zone, which is more fine grain have and more smaller structural noise. If we look at these red dots and start to reconstruct tomographic reconstruction of this, we see very precisely indications, which is not like to say very clear, and even you can get position. By the way, we check this also with tomographic X-ray, with X-ray tomography, and failed. Failed is because X-ray depends on density. Density of steel quite high. So higher density, the less resolution. These reflectors or some non-uniformities are very tiny. It's maybe I expect that it's some tens of micrometers, maybe cavities. So it's impossible to obtain sufficient resolution. And afterwards, from this, it's possible to create 3D image. And it was, by the way, this is noise where we suspected that it's already damaged by creep. And this is metallographic analysis of the same sample. You see that as fitting, there's a small cracks, and I will zoom one. If we zoom this area, we're getting like this, and you can see this distance is 200 micrometers. So you detecting quite tiny things using, in principle, just signal processing. Thank you. Questions?
Please ask your questions. We have several minutes, maybe a few minutes. No questions?
Too clear.
Okay, then thank
Okay.
you. It's
Thank
time
you.
for lunch because
Thank you.
maybe it's not that there is a